Hello everyone, welcome to this session. Thank you Professor for giving me this opportunity to present my slide here, and thank all class fellow for attending this session. This is Omar Faruk from Advanced Sensor and Energy Research Laboratory, and my academic supervisor is Professor Jae-Young Park. And in this session I'd like to discuss about review of MMIC technology. So through this session I will discuss about introduction to MMIC technology, then definition and history of MMIC, then field of application of MMIC, then material and device of MMIC, MMIC active device and passive device finally. So first of all, what is MMIC? So mainly monolithic microwave indicated circuit, or MMIC, is a type of indicated circuit device that operate at microwave frequency. And in MMIC, the operating range of frequency can be from 1 gigahertz to 100 gigahertz, which allow this technology to be applied to all of wireless communication system. So here you can see just two picture of MMIC like things. So just skip these things. And secondly, applications frequency range. So here you can see frequency range. So frequency range here, and here the application. So mainly application dependent frequency range is tabulated here. So this is very clear. So this is 3 kilohertz to 3000 gigahertz is tabulated here. 3 to 30 kilohertz for marine communication, 30 to 300 kilohertz for wireless station, 300 kilohertz to 3000 kilohertz for Intel ASF communication, 300 to 30 megahertz for amateur radio, and 30 to 900 for FM, TV, BPAR, etc. 300 to 3000 megahertz for mobile communication satellite, and 3 to 30 for satellite communication, and so on. And here commercial use of frequency range is tabulated. So this is in cellular or other application, what frequency range is required for transmission and receiving. So this is here. And the history. So mainly history subdivided into four things, that is early development, then introduction of compound semiconductor, then commercialization of expansion, then current trend and future interaction. So it's mainly start from by the invention of transistor in 1947, subsequent advancement in semiconductor technology, late current etc. And in 1960, the concept of integrating microwave function onto a single semiconductor substrate was explored as microwave technology became increasingly important for military and space application. And finally, we just in 1980, commercialization and expansion is expand, and this decade saw the first commercial MMIC driven by advancement in fabrication technology and the growing demand for telecommunication and radar system. And current trend and future direction is the integration of digital and analog function onto MMIC is becoming more common, moving toward a true system on chip solution. So this is overall history. And in this slide, a comparison between MMIC and hybrid MMIC is presented. So the merits of MMIC and hybrid MMIC is here presented. So in case of MMIC, there are several merits and advantages. That is non-returning engineering, cost is very high, then size and weight are very small, mass production cost is very low, very good design flexibility. Whereas for hybrid MIC, cost is very low, size and weight is very large, mass production cost is very high. So from this we can understand. So MMIC have some advantage, disadvantage. Hybrid MICs also have some advantage and disadvantage. So finally, in this slide, we'll discuss about advantage and disadvantage of MMIC. That is, main advantage is mass production cost is low, but requires significant investment to develop. But disadvantage is state of art performance is not possible. Complex MMIC have poor yield due to multi-capacitive effect. And here for hybrid MIC, advantage is much more better than MMIC. So cost is very low for simple circuit and requires a comparatively a small investment to develop. Size can be a small and embedded passive component, can choose the best transistor and etc. And its most important disadvantages does not have good reproducibility and reliability due to hand tuning and etc. Then application field of MMIC. So various field in various field MMIC is applied for. So for military, space, civil, everywhere actually we use nowadays the MMIC. So here tabulated you can see and you can read through these things. I just skip for time things. And finally the material and device used in MMIC. So material is mainly substrate material used here. This is silicon, gallium arsenide, silicon germanium, or silicon carbide. And active device is gallium arsenide MESFET, gallium arsenide HEMT, 3 to 5 SBT, silicon germanium SBT, silicon bipolar junction transistor, and silicon CMOS. And in case of passive device, here included inductor, capacitor, resistor, transmitter line, divider, combiner, isolator, via hose, air bridge, metal and wire bonding, and pads etc. So if we go into detail, then material used in MMIC is numerous semiconductor compound material are used in MMIC. So one is the group 3 to 5 compound such as like this, and group 4 element compound of group 4 elements such as silicon carbide and silicon germanium, all of which are used in MMIC. So for example, we are describing here gallium arsenide. So gallium arsenide is a alloy that used as the substrate material for manufacturing semiconductor chip. So it can operate more than 5 times faster than those made from silicon. There's a higher saturated electron velocity and lower field mobility than silicon, and the high resistivity of gallium arsenide makes it suitable substrate for manufacturing microwave component. And gallium arsenide device generate less noise than silicon device, and that is important for radar system and fiber optics. And an important advantage of gallium arsenide device is that they have lower power dissipation. Then secondly, silicon. So silicon is most popular substrate material used in chip manufacturing, and its element found in group 4, and which is abundant element in earth crust. And in comparison with gallium arsenide, silicon has high strength, allowing for easier processing and an excellent passivation layer suitable for planar integrated circuit. Low cost 12 silicon devices are obtained as a result of high yield. And thirdly, silicon germanium. The concept of combining silicon germanium to form an alloy for use in a band gap engineer transistor was envisioned by Shockley in 1951. Germanium is very similar to silicon, but it has faster and higher performance. Mobility is high, better than silicon. Thermal conductivity is better than gallium arsenide, and cost is low. And gallium nitride, it also have some advantage, and that is shown here. I just skip these things to. And device used in MMIC. Active devices gallium arsenide MESFET, gallium arsenide HEMT, gallium nitride HEMT, 3 to 5 compound SBT, silicon germanium SBT, silicon bipolar junction transistor, silicon CMOS. So here the 3 to 5 component HBT, 3 to 5 component HBT is actually a modified version of BJT with a wide bandgap emitter and a narrow bandgap base region. A schematic cross section is applied in figure. Here you can see, and silicon bipolar junction test high performance can be fabricated with a FT up to 25 gigahertz. The typical feature of such device include emitter width of 0.4 micrometer and the double poly self-aligned technique, sidewall spacer technique, buried layer, and selective decollector. And this is the schematic diagram of high performance silicon BJT. And passive device includes inductor, as I mentioned before. So MMIC inductor can be realized using a straight narrow track single loop inductor or multi-turn spiral inductor, and considering microstrip ribbon inductor with its equivalent circuit shown in figure here. And the inductance and shunt in capacitance can be calculated using the following equation. You can see here the choice of inductor is dependent on the required L and its implementation in the circuit. Capacitor. So MMIC capacitor, which has high capacitance per unit area and interdigital capacitor, can be used in MMIC. This capacitor is composed of two metal plates separated by a dielectric material, and you can see here MIM capacitor, and here the interdigital electrode capacitor. So resistor are used for feedback circuit setting the bias point of active device. So this is very normal, and we know R equal rho L, rho L bhag A divided by A, and A is width into thickness. Then important parameter is transmission line. So what is transmission line? Transmission line and waveguide can be defined as devices used to guide energy from one point to another, and transmission line can consist of a set of conductor, dielectric, or combination. So here you can see the uh, transmission line. However, the transmission line are almost always microstrip for MMIC purpose, although coplanar waveguide transmission line have been used as shown in figure here. And here isolator and circulator. So this is almost same things. So an isolator allows an microwave signal to pass in one direction but not in the other, which can achieved by using ferrite. And a circulator route the microwave signal from one port of the device to another. So this is basic difference. And what is via hole? So via hole are used to microelectronics to connect different metal layer in integrated circuit, but also can be used to electrically connect both sides of silicon wafer. So this so-called through wafer hole or via hole can be used in broad range of applications such as three-dimensional packaging, microelectrochemical, electromechanical system or MEMS, or multi-chip stacking. Here on via hole is shown. And what is metal air bridge? So air bridge or crossover are required for most MMIC layout. And an air bridge is simply a metallic bridge that permit two transmission line to cross over each other without the formation of electrical short circuit. So here you can see on metal bridge. And the last topic is wire bonding and bond pads. And so what is this? So interconnection is necessary between MMIC and accomplished by wire bonding, right? So bond pads are provided to allow wire bonding for electrical connection. So through the wire bonding and band pad, DC bias can be supplied and output signal can be taken out, right? So there is an alternative technology that is called flip-flop method. So solder bump are used rather than wire bonding, and this bump avoid low pass characteristics of the wire bonding connection. And The series inductor and shunt capacitance can be reduced by using this flip-flop technology. And here you can see two types of interconnection technology. One is wire bonding and another is flip-flop technology. So this is all from my side. Thank you for your attention.